In this lesson, we'll talk about properties of logarithms. Let's recall from the previous lecture these 4 facts. Any logarithm with base b of 1 is always 0 because b to the 0 is equal to 1. Any logarithm with base b of the same b is equal to 1 because b to the 1 is b. Logarithm with base b from b to the x, we can basically forget about log and the base b and leave it with x because b to the x is b to the x. And similarly, if we compose exponential function and logarithmic with the same basis, then they annihilate each other and we are left with just x. We're going to develop more very important properties that makes logarithms very attractive when solving equations. Because as you will see, logarithms simplify operations from multiplication to addition, from division to subtraction, from power to multiplication. So they are very useful. How do we know about those properties? Well, since logarithms are inverses of exponential functions, the properties of logarithms arise directly from the properties of exponents. To see it clearly, for any real positive numbers x and y, let's assign values log base b from x as p and log base b from y as q. This is just to make the calculation a little bit easier because we'll use simple letters rather than this long expression. These two equations we can translate into exponential form as we learned last class. So the first equation is b to the p is equal to x. It's here. And the second equation, b to the q is equal to y over there. Okay, so we can use these 4 facts in order to prove the following properties. Those are very important properties. You really need to learn them well. Log of a product is a sum of logs. Log of a quotient is a difference of logs. And log of a power is your power times the single log. So to remember the last property, you can think I can take the exponent outside of the log, like here. Okay, let's try to prove those properties. Start with the conversion log of product into sum of logs. Well, if we start with the product x times y, and x is b to the p, and y is b to the q. But if we multiply powers with the same basis, we're supposed to add exponents. Okay, but what's p plus q? P plus q is the same as log x plus log y. So now it's enough to apply log to both sides of this equation. Therefore, we have log xy, which is here, equals to log b to the p plus q, which is over there. And since log with base b cancels the exponential base b, then you're left over with p plus q. But what's p plus q? Let's go back to our substitution. P plus q is the same as log b from x plus log b from y. So yes, we really proved the equation that log of a product is equal to sum of logs, this first property. Now I will suggest that you stop the video and you try to prove the second property by yourself. It should go very similar way, so let's try it. Okay, I hope you already tried this, so now I will show you the proof and you can just check if everything went fine. So let's start with the quotient x over y. Similarly as before, x is b to the p, y is b to the q. And then we use the properties of exponents, keep the same base and subtract exponents, p minus q. Now let's apply log on both sides of the equation. So we end up with log b from x over y equals log b from b to the p minus q. But that means the same as p minus q. And we know that p is log b from x, and we subtract log b from y. So yes, indeed, we have this property. Finally, to prove the last property that we can actually take n out of the log, we start with x to the n as before, and instead of x we'll write b to the p, so your x is b to the p, and then it's raised to the n. Now if we apply log to both sides of the equation, we have log base b from x to the n equals log base b from b to the pn. But log base b with the exponential function with the same base annihilate each other, so we end up with just pn. Therefore, we really have this equation, log base b from x to the n equals n times p, which is the same as n times, and our p was log base b of x. So yes, indeed, we have this property. We can always take the exponent outside of the log. Notice that for integer n, this property arises directly from the previous two. For example, if n is natural number, particularly 2, then log base b from x to the 2 is the same as log base b from x times x. But then we can use the first property and we can split this log, so it's a sum of two logs, log base bx plus the same log of x again, which is the same as 2 log base b from x. So yes, we can actually take this exponent 2 and bring it outside of the log. So that's another way of showing that this property is true. However, that works only for integers, and the proof that I showed you on the right hand side works for any real n. We really have to be careful not to get confused with those properties. We don't have a property that splits log over addition or subtraction. This is never true. This is not true. So don't confuse this with the splitting of log over multiplication into addition and division into subtraction. So remember, log simplifies operation from multiplication to addition, from division to subtraction, but logs do not split over addition or subtraction. Let's use the above properties of logarithms to rewrite this expression log of something complicated in terms of logarithms of just x or y. Okay, we can start with log 2 root y over x to the 4. So we have log of a quotient. The most outside operation in this expression is a quotient. So we can split log of a quotient into difference of logs. Log 2 root y minus log x to the 4. But then in the first expression we have log of a product. So we can split this into the sum of logs. So we have log 2 plus log root y. Then we have minus, and then we have log of a power. Remember, we can take the exponent outside of the log. So we can rewrite it as 4 log x. And finally, root of y is the same as y to the 1/2. So the exponent 1/2 we can actually take outside of the log again. So our final expression will look like that. Log 2 plus, take the 1/2 out as an exponent, log of y, and minus 4 log of x. Notice that in this expression, the log of 2 is a known number. You can always evaluate it using calculator, but we don't have to do it. It's better to leave it in an exact form. And here we refer just to log of y and log of x. So we comply with the requirements of the problem. In the next problem, we need to go the other way around. We need to fold back this big expression into single logarithm. So again, using our properties, let's start bringing all the coefficients inside of the lns as an exponent. So instead of 5 ln x, I can write ln x to the 5. Then the 2 will become the exponent, so it's ln bracket square. And minus 1/2 will become exponent 1/2, which is the same as root. So minus ln root of x minus 1. And then let's put together the first two lns. Sum of lns is a ln of a product. So it's ln of a product, x to the 5 times the bracket x plus 2 square. And then we have subtraction. Finally, this subtraction translates into quotient. So to place it under 1 ln, we have the numerator x to the 5 x plus 2 square and denominator square root of x minus 1. And the question is done. So in this section, you really have to practice a lot of questions like that to be fluent in conversion from the single expression, split it into expressions that involve logs of particular variable, or from the big expression, change it to the single log. Now let's try to solve this simple exponential equation. Notice that here we can't really guess the x, because there's no nice power of 2 that will make it 10. That will be some unpleasant number. But in terms of logs, we can express this exactly. Okay, let's solve this equation in two different ways. First, applying log with base 2 to both sides of the equation. We can always do that because logs are one-to-one functions. So this statement and the statement log base 2 from 2 to the x equals log base 2 from 10 are equivalent. However, if I see log base 2 from 2 to the x, this 2 annihilates the log 2 and we are left with just x. Therefore, we actually solved for x. X is equal log base 2 from 10. Well, this is the exact solution. We can't really find out at that moment how much approximately is that because we don't have the button on the calculator with log base 2. However, we have buttons with log base 10 or ln. And we'll see how can we use the other buttons to evaluate this pretty soon. For now, let's try to solve this equation applying log to both sides with the base 10 rather than base 2, because we could really apply any log that we wish. Obviously, with base 2 we had the advantage that we could reduce the bases and isolate the x by itself. How does this work with log? Well, let's see. Log of 2x equals log of 10. Oh, so this time we have advantage on the right hand side because log of 10 is easy to evaluate. This is simply 1 because 10 to the 1 is 10, right? However, on the left hand side we can drop the exponent out of the log and then we have just log 2. Therefore, we can solve for x by dividing by log 2. This is equal 1 over log 2. And this time we are able to evaluate. We can use calculator and divide 1 by log 2 equals, and that's approximately 3.3219. Please check on that by yourself. Okay, let's look at our two solutions. How did we evaluate x on the right hand side? This one was really the same as log 10. So we've got log 10 divided by log 2. Both of these expressions we are able to evaluate using our calculator. We have the button of log. So plug it into the calculator. Instead of 1 over log 2, write down log 10 divided by log 2. On the other hand, the x is equal to log with base 2 from 10. So these two expressions really mean the same number. Why it is so? Because the exponential function is one-to-one, therefore we can have only one solution. So x obtained by this way of solving and by that way of solving must be the same. Okay, well, if we observe what's going on here, the 10 is in the top, the 2 is in the bottom. Maybe we can develop similar formula for logs with any bases to convert it to the base 10 or base 2 or any other base. You may want to check that this is the same as ln 10 over ln 2. Well, use your calculator and check if that's true. Generally, we have the formula that allows us to convert bases. So if we have log with certain base b from a, we can always rewrite this in terms of log of particular base c that is desired, for example, base 10 or base e. So this is the same as ln a over ln b. Okay, therefore from now on we can actually use calculator to evaluate logs with any bases, not only 10 and e. And well, let's try it. Evaluate each logarithm, round the answer to 3 decimal places. Plug it into your calculator log base 5 from 10. How do you do that? By saying this is the same as log 10 divided by log 5. Obviously log 10 we know it's 1, but even if this number will be different, you can always do it that way. Okay, and we should end up with approximately 1.43, and the third digit will be 0. Second expression, log base root 2 from e. Well, you could even use ln to make it easier. You can say ln e over ln root 2. And then evaluate this. The approximate number is 2.885 when you round to 3 places. Finally, log base pi from 1/2. So see, your bases could be as ugly as you only can think of, and we can still evaluate this. So I like to use ln, so let's put ln 1/2 or 0.5 over ln of pi. And this is approximately negative 0.606 when you round to 3 places. Check by yourself. Now we have a couple questions to evaluate without a calculator. That means we need to use properties that we know. And the first question is kind of interesting. We have log base 2 from 3 times log base 3 from 4, and the pattern repeats, so the next one will be log base 4 from 5, and so on till we end up with log base 15 from 16. The bases are changing and the inputs are changing. What could we do? Let's see what will happen if I will change all the logs into the base 2. So the first one, rewrite as it is. The second one, it will be log base 2 from 4 over log base 2 from 3. The following one, log base 2 from 5, log base 2 from 4. Oh, I see some pattern. You see those logs from 3, from 4, from 5, and so on, they will cancel each other. So this cancels that, this cancels that, this will cancel the following one that is not written. And just observe the last two. Well, the previous one will be log 15 over log 14, and the last one is log 16 over log 15. So as you see, the 15 will be cancelled. The 14 was cancelled with the previous one. What's really left is just log base 2 from 16. So we really end up with log base 2 from 16. 2 to what exponent is 16? Well, it's 4. 2 to the 4 is 16, so this log is 4. Okay, let's see what's going on in the second example. This time we have log base 5, and here we have log base 25. And there's another log base 5. So these two logs we can't really combine as they are right now, because they have different bases. So what could we do? Well, let's take care of this base 25, rewrite it in terms of base 5, and then see how can we simplify the rest. So we have log base 5 from 1/2 plus log base 5 from 4 over log base 5 from 25, which is 5 square. Everything over log base 5 from 2. So now this log base 5 from 5 square is actually equal to 2. So we can replace this by 2, or rather take 1/2 in front of the log base 5. Okay, that will look like log base 5 from 1/2 plus 1/2 log base 5 from 4 over log 5 from 2. Okay, but now we can take this 1/2 and bring it inside the log as an exponent. So 4 to the exponent 1/2 is like square root of 4, which is really the same as 2. Therefore, we have log base 5 from 1/2 plus log base 5 from 2 over log base 5 from 2 as well. Okay, now we can use the addition of logs, bring it into single log base 5 from the product of 1/2 times 2. So we have log base 5 from 1/2 times 2, which is really 1, over log base 5 from 2. Okay, so log base 5 from 1 is actually 0. 0 over log 5 from 2 is still 0. So all this expression is equal to 0. And the last example, here we have e to ln. Oh, that would be good if we wouldn't have the -2. So what we need to do is bring this -2 inside the ln as an exponent. So this would be e to the ln of 3 to the -2. Okay, but e and ln cancel each other, so we really have 3 to the -2, which end up to be 1 over 3 square, which is 1 over 9. And as a practice, you have another property of logs. Remember, if we have exponent n by the x, we could take it outside of the log. But if we have exponent by the base, we can still take it out, but as a reciprocal of n. So that's another formula, very useful formula. For example, in the previous case when we had this 25, if we knew this formula, we could take this exponent 2, because that's like 5 square. So instead of exponent 2, we could directly write 1/2 in front. And that's what happened, but a little bit longer. Anyhow, that's the property that I will ask you to stop the video and try to prove by yourself before I do that on the video. So use change of base formula to prove this property. Let's start with the left-hand side, log with base a to the n from x. So be very careful when you write different levels, because this is still base, but with an exponent. Okay, let's change the base into base a. So we have log base a from the top, which is x, over log base a from the bottom, which is a to the n. And then you will see that from the bottom, I could take the exponent outside of the log because we already have this property. So pull the exponent down, log a from a, and the top copy it as it is. Then log with base a from a is equal to 1. Therefore, we have 1 over n. So yes, we did prove the property. It is the same as the right-hand side. In the next practice problem, well, if it's practice, again, I would ask you to try on your own first, and then continue with the video to confirm if what you've done is correct. We need to graph log with base 5 from something without the aid of the calculator. How can we do that? First of all, I would think about checking the domain. Anytime you have some graphs to do, check the domain. So what's domain of f? Our input must be positive, and it is squared, but it can't be 0, therefore x can't be -2. Therefore domain is all real numbers but not -2. That means the graph will just miss the -2 from the domain. The rest of the x-axis should have some values. Now observe that if I will be able to graph log with base 5 from x squared, then to obtain the graph of f, log base 5 from x plus 2 squared, it's enough to use translation of the original graph by the vector -2, 0, so 2 steps to the left. Therefore our task is narrowed down to graph log base 5 from x squared. But how can I graph log base 5 from x squared? Maybe the fact that I can take the 2 outside of the log would help, because then I know that log base 5 from x comes through 1, 0 and then 5, 1. However, it will be multiplied by 2, so it's 5 times 2. And also I have the y-axis as vertical asymptote, so the graph will have this shape. But as you see, these two functions are the same only in the common domain, in positive numbers. However, the first function, log base 5 from x squared, has a domain or real numbers except for 0. And it's easy to check that this function is even. Since it's even, then it's enough to bring this shape to the other side. So this point will be reflected here, that one over there, and graph. Great, so the blue one is the graph of the function ln 5 from x squared. Well, let's go back to the function f. Let's graph this in purple. That will be the same shape as log base 5 from x squared, but moved 2 steps to the left. So the vertical asymptote, that was y-axis, now it comes exactly through the point -2. That's why -2 is out of the domain. And the shape proceeds as follows. This point is here, that point moves 2 steps over there. We can volunteer a shape like this. And the second branch, this point is moved here, that one over there, and we graph it. So the purple graph, that's a graph of f of x. Since our question really called for graphing this function by using a graphing calculator, let's see how this can be done with the aid of a calculator. We need to graph log with base 5. So we need to convert this base 5 to some other logs. For example, I used ln. So that's how we can enter the function to the calculator. ln, open a bracket, x plus 2 squared. We need to close this bracket. Remember to close that bracket. Divide by ln of 5. Again, we need to close this bracket. I already prepared a window from -5 to 5, so let's just graph in the window -5 to 5, and on y-axis also -5 to 5. As you see, we do have the same graph. We have the vertical asymptote at -2, and we can check some other points. For example, the value of the graph at 3 seems to be 2. So all those points really match our findings. Also, the intercepts are at -3 and -1. So it's exactly the same as we graphed without the calculator. And finally, logarithms are quite often used in application problems. For example, Richter scale is based on logarithms. It was developed to measure and compare very large or very small numbers, because if we apply logarithm to small numbers that differs very low, the differences in logs will be quite extensive. They will show up a lot more. However, to apply logarithm to very large numbers, they may not differ so much, so we can see those differences a little bit better. Okay, how Richter scale works. The magnitude m of an earthquake with an intensity I is measured in reference to a zero-level earthquake of intensity I0. So certain type of earthquake is assumed to be the normal zero-level type, and the magnitude of some other earthquake is measured in reference to this normal shake. By using this formula, the magnitude is log of the quotient I over I0. So even if I over I0 is very large, when we take log of it, it may not be so large, and it's easier to handle. Using this information, let's solve the following problem. How many times as great was the intensity of the 1960 earthquake in Chile, which measured 9.5 on the Richter scale, than the San Francisco earthquake of 1906, which measured 8.3 on the Richter scale? So let's I, with the subindex 1960, represent the intensity of the 1960 earthquake, and I, with the subindex 1906, intensity of the San Francisco earthquake in 1906. So let this be intensity of quakes in 1960 and 1906 correspondingly. Then, well, we know that this intensity was 9.5 on Richter scale, which means that 9.5 instead of m is equal log of I 1960 over I0. Also, the second one, 8.3, equals log of I 1906 over I0. That's what we know. What do we want is the ratio between I 1960 and I 1906, because we want to know how many times this is greater than that. Okay, so we're really looking for the ratio between those inputs. To find out the ratio, it's enough to subtract the logs. So if I will go 9.5 minus 8.3, which is different on the left-hand side of these two equations, and then I subtract the logs, then it's the same as the log of the quotient. But the quotient is I of 1960 divided by I0, then divide by, which means multiply by reciprocal of I0 over I 1906. That's the same as the quotient. However, as you notice, the I0 can be reduced, and yes, we end up with the quotient. The only thing that we still need to do is to get rid of this log. So how do we get rid of log? By placing the base 10 underneath. Then this base 10 will cancel the log, and we end up with whatever we wanted. So, starting with the right hand side, we really have the quotient I 1960 over I 1906 equals the left hand side, and this is 10 to the 9.5 minus 8.3 is 1.2, so 10 to 1.2. And using calculator, this is approximately 15.8 times larger. So the earthquake in 1960 is about 15.8, nearly 16 times larger than the earthquake in 1906. However, the Richter scale didn't differ too much. It was just 1.2 larger. So a tiny differences on Richter scale actually represent quite larger earthquakes.